Hi, thank you for coming. Today I'm going to share our experience of how to build and operate a real-time driving school service using Flink. And I'm Dongwon Kim from SK Telecom. And this is my third appearance at this event. 2015, I came here to compare the performance of famous batch processing engines like MapReduce, Spark, and Flink. And last year, I came here to present our predictive maintenance solution using deep learning and Flink. And this year, I want to tell you a very interesting service in our mobile navigation app called TMap. TMap is like Waze and Google Maps. And from the main screen, you can enter an address or a place name you want to go, or you can choose from based on your history, choose from frequent locations. And let me go home, okay? And it suggests multiple route options and choose one, and it guides you to the destination. As such, it is essentially a navigation app. Besides the essential route guidance function, this TMap provides a very interesting service, which is called a driving score service. Here, 83 means I scored 83 out of 100 points. And we are collaborating with insurance companies on providing car insurance discount to drivers with high driving scores. And okay, let's see it. And driving score is based on three factors. First, speeding, and second, rapid acceleration, and third, rapid deceleration. Driving score is calculated by these three factors, and let's see my driving history, history of driving scores on June. And the three factors are calculated by each session. Here, I have two driving sessions on June 29th. And as you can see here, each of the two sessions has three factors here. And likewise, I have two driving sessions June 28th. And on that morning, I violated all the three factors. One speeding, one rapid acceleration, one rapid deceleration. And let's see what happens on that day. This road, the speed limit was 70 km per hour, but I drove 90 km per hour. And it shows where I rapidly accelerated this way, and it shows where I rapidly decelerated. And to do that, I'm going to tell you the current client-server architecture to do that. TMap generates a GPS trajectory for each driving session. A GPS trajectory is a sequence of timestamped GPS coordinates. And for all users' driving sessions for a single day, we execute batch ETL jobs twice a day to calculate the three factors from the trajectories. And users can see their three factors and driving scores. But the main drawback of this batch-oriented architecture is that user cannot see today's driving scores until tomorrow. So we decided to migrate the service from batch ETL to real-time streaming processing using Flink. And the goal is obviously to let users know driving scores as soon as they reach their destinations. Okay, so Flink serves our purposes very well with the features shown in this slide. Okay. First of all, I'm going to show you the data flow design and how we customize the trigger to meet our purpose. And then I will show you how we do instrumentation with Prometheus. Okay. TMap generates a GPS coordinate every second. Then for a 12-minute driving, we will have 720 GPS coordinates. Instead of sending these individual GPS coordinates to the service server, we send just 4 messages like this. We first send an any message which contains no GPS coordinate. And then after 5 minutes, we send the first periodic message which contains 300 coordinates for the first 5 minutes. And then after another 5 minutes, we send the second periodic message which contains 300 coordinates for the next 5 minutes. And then finally, we send an end message which contains 120 coordinates for the last 2 minutes, and which signifies the end of a session. So what I want to do is return scores right after receiving the end message, 720, 720. And so to that end, we design this data flow. First we have a source here to read data from Kafka, and we add a process function here to parse JSON formatted string into the internal representation. And then we have a session window here where we use a combination of user ID and destination as a key. And our session gap is 1 hour here. And one thing to notice here is that we define a custom trigger to get early result. I'm gonna tell you this in the next slide. And then as the sliding window is working based on event time, we need to add timestamp extractor beforehand. And the data are coming out of order. We decided to use bounded out of orderness timestamp extractor here. And lastly, we have a sync to write result to Kafka. And here we use at least once Kafka producer because we need very low latency and we don't need end-to-end exactly one semantic. So we decided to use that. And this is the physical data flow. And here for the source, JSON parser, and timestamp extractor tasks, we have a parallelism of 20. This is because our input topic consists of 20 partitions. And then after keyby, we have 255 tasks for session window. This is to use as much processing power as possible available in our cluster. Okay, let me show you why we define a custom trigger by comparing the default implementation and ours. Okay, say when an input message comes in, it is assigned to its own window. And the size of the window equals to the session gap, which is 1 hour in our application. And the trigger registers a timer at the end of each window. And then when the first periodic message comes in, it is also assigned to its own window. But soon, 2 windows are merged into a larger window. And when 2 windows are merged, the previous timer is removed and a new timer is registered at the end of the new window. And then the second periodic message comes in and same thing happens. And the last message comes in and the same thing happens. And this trigger fires when this watermark reaches the timer, which is 8:20. This is 1 hour after I reached my destination. Then we will have 3 factors from all of the 4 messages. That's not enough, so we decided to define our custom trigger here. Here we have already 3 messages in a window and a timer registered at the end of the window. And when the last end message comes in, a merge occurs very much like the default trigger. And here we register an early timer here using the timestamp of this end message. And this custom trigger fires when the watermark reaches the early timer. And we get the complete result 1 hour earlier than this default one. And when the watermark advances to the original timer, we do not fire because nothing has added to this window after the early fire. In this way, we are trying to avoid producing same output multiple times. And then, okay, this timer seems unnecessary, but it is really necessary for the case of out of order messages. Let me show you that. This slide shows an example of out-of-order messages for the same user. Okay, here A and B passing through the default partitions, and they are gathered to the same window task here, because these are from my phone. And we have, while the second periodic message generated earlier than D, C got stuck somewhere, and D comes at the Q earlier than C. Then C comes in. In this case, we will say out-of-order messages happen. And let's see how our custom trigger deals with that case. There can be two additional cases. Let me show you that. We have two messages, and then D comes in, and then we register an early timer here using the timestamp of this end messaging. And then before the early timer expires and C comes in, then watermark reach this timer. Then this time we have a perfect result, but although we have some kind of out of orderness here, we can calculate the correct result by sorting them. And then we do not fire here. But in this case, when it comes in, we have an early timer here, and then the watermark reaches the early timer before C comes in. In this case, we have an incomplete result. We calculate the three factors only from three messages, not from four messages. And then C comes in, and then this time, this timer is very necessary because we need to anyway have to calculate the correct result from the four messages. And this is the actual implementation, and it is a major part of our implementation, and you can see the whole source code from this link. And the shaded regions are the difference to the default event time trigger. The constructor takes an evaluator to determine early firing, and then the evaluator is used in on-element method. If the evaluator returns true, this custom trigger registers an early timer. And in my application, when the end message comes in, the evaluator returns true. And as the early timer is always smaller than the max timestamp, we add these lines to fire if the early timer expires. Okay, I've covered this one, and then let's see how we do instrumentation with Prometheus. Well, to have individual message statistics, we add the following operator down the JSON parser. And their physical data flow looks like this. And one thing to notice here is that we set the parallelism of this message statistic to 1. This is because we want to expose jam level metrics, but they cannot be defined in a distributed manner, and they cannot be merged by external metric systems or dashboards because it will lead to incorrect statistics. So we set to the parallelism to 1 here, and then through this message statistic, we expose messages per second and input bytes per second, and then message size quantiles and jitter quantiles. And let's take a look at the last one. We define jitter as the difference between event time and ingestion time. And if you take a closer look at this chart, you can see that 0.95 is around 1 second. And based on this observation, we use 1 second for the argument of this bounded out of orderness timestamp extractor. And then these are for individual message statistics. And to have session output statistics, we have following operators down the session window here. and their physical data flow looks like this. And likewise, this session output stat sync also has a parallelism of 1 for the same region. And through the stat sync, we expose session output per second and output bytes per second. And this is session output size quantiles, and this is latency quantiles. And let's look at the last metric. We have our own definition of latency, which is the difference between ingestion time of end message and the processing time of the resultant session output at the extractor. And here, considering our max out of orderness, which is 1 second, Flink takes at most 250 milliseconds here. 0.999 is around here, and at most 1.25 minus 1 second is 250 milliseconds. So Flink is quite nice. We can guarantee very low latency using this pipeline. And then lastly, let's see how to expose metrics to the Prometheus. Well, Flink provides various metric reporters, and among them, Prometheus reporter is somewhat different from others. Ganglia reporters periodically push metrics to Ganglia daemons, and Graphite reporters also push metrics to Graphite servers. But this time, Prometheus reporters just open HTTP endpoint, and it is Prometheus who scraps the metric from the endpoint. While these two reporters require to specify server addresses to push metrics to, the Prometheus reporter requires a port number so that it can open an endpoint. And to accommodate multiple Prometheus reporters on the same node, you need to specify a port range instead of a single port number. And what I want to tell you in this slide is that endpoint addresses cannot be determined in advance. Say you have a Hadoop cluster consisting of 4 worker nodes, and you want to launch a Flink cluster consisting of 4 task managers. And you specify to use this port range for Prometheus reporters. Then here is a quick quiz. And can you list the endpoint addresses at this point before Yan scheduling task managers and job managers? The answer is no, it is impossible, because there can be multiple possible worlds depending on where a job manager is scheduled. It depends on situation. And when you launch another Flink cluster, things are getting complicated. So endpoint addresses are available, as I showed in the previous slide, after a cluster is up. Then how can you let Prometheus know where to scrap metrics from? There is a Firebased service discovery mechanism in Prometheus. And when you configure Prometheus in this way, Prometheus watches file names matching a given file pattern under this directory. Then when a new cluster is up, you just need to write this file, this JSON file, to let Prometheus know where to scrap metric from. And for another cluster, you need to do the same thing. And then Prometheus will scrap metrics from known endpoint in this way. However, the procedure is somewhat manual. So I'm trying to automate this process by making a script. And you can see the script from my GitHub repository. And if you are using Yan for deploying your Flink cluster, and you are using Prometheus for your instrumentation, I think this script will help you a lot. Okay, and because I'm running out of time, it just watches Yan for your cluster, and it scraps job manager and task manager logs instead of you automatically. and it create a file, and then Prometheus can see this new cluster. Okay, now that we have metrics in Prometheus, you can see this graph on the dashboard. And okay, Flink is working very well without any restart. Okay, up to now I've covered our data flow design and how we do instrumentation with Prometheus. Okay, I have no time, so if you have questions, come to me in person. Okay, thank you.